We talked about energy stored in the capacitor yesterday. We talked about parallel plates. The work done to move charge across the parallel plate. This is not, this is me just going, David, turn around. The work done, W equals QV. And when you're talking about parallel plates, I want you to think about the plates being quite far apart. Okay, they don't really have any space to store anything. They might have air between them. They might have any type of gas between them. There's no place for charge to be stored. It's just two parallel plates. When we did, when we like a TV tube or something, which you get something where you've got parallel plates, the plates can be centimetres apart. There's air between them. You ain't going to store charge in air. So think about it that wide. And you've got W equals QV as the work done, is the charge you're going to place, and the potential difference across it. Notice how I'm using the word potential difference here instead of using voltage, because its potential difference is different from EMF or TPD. Potential difference is a difference in potential across something. Then we look at a capacitor. Capacitor, I want to think about it as being a lot closer together. Similar to parallel plates, David. Similar to parallel plates, but you've got this material between them that allows charge to be stored. The more charge we put onto the plates, the greater the potential difference that's now appearing across the plates. Now, what I want you to think of a capacitor like is like a battery. You're storing charge. A battery is like a fancy capacitor, like a chemical capacitor. It is stored charge inside it, and it has charge built up in one side and charge built up in the other. So we are going to store charge. The more charge we put into it, the more potential difference that's across it. So the more charge we put into it, the more potential difference, and you get this linear relationship. This linear relationship, if we want to know how much energy, and from our parallel plates we know that energy is charge times voltage, but this time, because you get this linear relationship, energy is equal to half QV, and don't get these two mixed up. Very, very common mistake. If anyone does that, I'll be annoyed, because I'm telling you, don't do it, because it's really, really, really common that people do that, and it's something I'm trying to point out to you so you don't do it. Right, so what do I mean by a capacitor a bit like a battery? Well, a cell in a battery would look like that. Negative side and positive side. Inside your cell, you've obviously got charge coming out. You've got negative charge coming out here, negative charge coming in here. And if you think about it a different way, you've got positive charge coming out here and negative charge coming out here. And they go round and they swap places, and they go round in a circle. Okay, they go round in your circuit. If you think of a capacitor has charge getting built up on either side. You've got negative charge getting built up on one side, you've got positive charge getting built up on the other side. And then once it gets to a certain point, the charge will balance itself out and stop building up in the plates. Now you're looking at what I have here. If I join these two together, so battery's giving out this negative, so negative's coming out and it's going into the capacitor and it's building up in the capacitor instead. It's then positive is coming out here and going on to the positive side of the plate. Now I put an arrow in here, this is for negative charge. It could be positive charge coming out that side and building up in the plate. Now if this battery was rated at 6 volts, then it's going to give out charge until it can't give out any more. Now I said to you it takes energy to build up charge in a plate. The more charge that comes round here, the more negative charge coming in, the harder it is to build up charge in the plate, because you've got this negative charge here opposing these charges coming down. There's more charge getting built up here, and the negative charges don't really want to get onto that plate. They're getting repelled by those negative charges, but this battery is just forcing them through. Okay? They're getting pushed out of here, out of the battery, until it can't push anymore. Alright? Now, it's not that funny. I don't know. Okay, so they're getting pushed onto this until they can't push anymore. Now, what is going to be this? You've got a negative on one side and a positive on the other. What are we building up on this capacitor? Between the plates, like either side of the capacitor, what are we building up? Charge, yeah, causing potential difference. You're going to have a negative potential on this side. You're going to have a positive potential on this side. So at some point, you're going to get a potential difference across this. Now at some point, what is the maximum potential difference that can be built up on this capacitor, James? If the maximum potential difference you get from the battery is 6, what's the maximum that can build up in the capacitor? 6. Not going to get any more than that. Now, okay, if potential difference is like the energy per coulomb of charge, then you've got current, which is flow. what's going to happen to the flow of the charge as the potential difference across the capacitor gets to 6 volts? Or when it gets to 6 volts, what are you going to find? Looking at the diagram here, when this gets to 6 here, and this gets to 6 here, then there's 6 and 6. This is trying to push electrons out this way. This is trying to push electrons out this way. But they both have the same energy, so they're going to come and they're going to meet, and nothing's going to happen. Positive's getting pushed out this way, positive's getting pushed out this way, and they're going to meet, and nothing's going to happen. So what is going to happen to the flow of charges when the potential difference across the capacitor gets to 6? Ross?
There'll be no flow.
There'll be no flow. The current will be 0. So, what type of circuit is this? AC or DC? Robert?
DC.
So, the current is changing direction every second.
DC.